So let's now look at the velocity distribution. Do you remember the velocity distribution needed to be okay, for 3-dimension, it's related to v squared e to the minus e over kbt. Okay, this is for 3D, but our system is 2D, two-dimensional. So two-dimensional distribution goes like this, and we mentioned it why, right? It has to do with the integral in 3D that involves 4 pi v squared dv, like, right? And in 2D it's 2 pi v dv. So this v comes here. Okay, let's check if indeed the velocities will settle in that distribution. So this time, whatever we did for the energy, we do for the velocities. I'm sorry for saying velocities. I'm talking about the speeds, the absolute values of the velocities. Okay. And here I even calculated the entropy. Just let me first draw what happened. I discovered a new thing in MATLAB, but anyways. So I will plot this distribution of speed. So let's run this, and the speeds approach to something that we expect. I think I had a code that had speed distribution too, but I couldn't find it. Well, never mind. You believe me, right? Energies were on top of each other, so speed should be also on top. Let's then start looking at the entropy. Okay, let's start by looking at the, and what do you expect for this system?
After it reaches the maximum entropy increasing equilibrium point, it will like increase in a uniform, not make linear, I don't know what.
So let's say I start,
yes.
And then what happens with the entropy? It would start increasing.
After some point, after it reaches the equilibrium, it would keep increasing in a more uniform.
Why it should keep increasing? You reach equilibrium.
The equilibrium in which entropy is the max, right?
Yes.
Yeah.
So it should start with some number for entropy, and it should reach that level. Well, let's then start with our crippled velocity distribution, like this one. So I'm saying crippled because it's a uniform distribution, and that's not the distribution of particles at all. Gaussian looks more like that, but you get what I mean, right? So how do I calculate the entropy? I calculate it numerically. Basically, first we look for the probability of being at a certain speed. Okay. Do you see the same trick used here? Yes, the normalization and divided by the d speed, delta speed. Then, how do you calculate entropy? Basically, for any probability that is above 0. So I avoid 0 probabilities because they will give undefined in MATLAB, right? 0 times ln 0 will give me none. So I avoid them by saying that, okay, sum up over the probabilities that are bigger than 0 and sum all p times ln p's, right? And finally multiply it with this d speed, because I want to get two things. First, integral of pv dv should be 1, and integral of minus pv ln pv dv has to give me the entropy. And furthermore, it has to be independent of dv that I'm using. That's a very important point. That's one of the reasons why Boltzmann was so harshly criticized. And I will come to that point, okay? Are you ready? I will run this. And you will see that the entropy starts with some number. And as the system runs, it reaches some equilibrium. And it stays there. Are you convinced?
Even numerically, would it oscillate forever in some values, or would it actually?
Yes, it actually oscillates. Let's close this and okay, no, it's not doing it. So let's see it exactly, and that's very important point. So do you see the oscillations?
Yes, but numerically, why doesn't it converge to a constant value? I don't get it. Yeah, still at some very, let's say, later time,
it will.
Should converge, shouldn't it?
Yes.
But would it?
It would. It will.
Even in this code.
Even in this code.
No,
I mean, you are talking about taking a lot of steps and averaging on a lot of steps. So right now we are looking at the moving average of 1,000 steps. Okay? How many steps? We didn't even reach our moving average yet. It's just 760. So no problem then, right? So this is entropy, by the way, derived from energy, and I define it over here. Entropy derived from energy distribution is, so you use P ln P of the energy, okay? So you can also define the entropy because of speed distribution, and it's P ln P as I just described. So let's draw both of them together. In principle, they should be the same, but probably I'm doing something wrong. But qualitatively, I'm happy with the way they are going. They are both approaching to some maximum value, etc. There will be much more problems in a moment, okay? I promise. So do you see that the system indeed has an entropy and it reaches some value? Do you have any questions so far? You have missed one of the most important parts. So we calculated the entropy numerically from the P ln P sum. Okay, now let's move to another entropy derived from the distribution of velocities in the distribution of velocities, not the speeds. So let me tell you what I mean. So one way of looking at probability is what is the probability of being at velocity v between the velocity v and v plus dv, right? So you get some pv. But we know that there can be different vx and vy values that correspond to the same velocity. Do you agree? So we are ignoring our ignorance about this. So we have to wake up and realize that there is more information that we are missing. Okay, how we do this now? We think of these Vx and Vy's. Vx and Vy's. Again, we discretize them and think of them as rooms where particles can sit or not sit, where there can be several particles or not. Okay, so and then we have some probability Vy, Vx, Vy, right? So we need to sum all of Px, P, Vx, Vy, ln, P, blah, blah, blah. Do you understand the point? So do you remember our hotel that had Q floors, yes, and like number of energy rooms? Now our hotel will still have Q floors, but think of each floor now two-dimensional. So you have Vx and Vy's, right? And there are rooms there. Then we will sum all them up and look at the probabilities. I'm actually doing the following. I'm taking this two-dimensional thing and making it a line. So I put this one over here and I attach this one over here. Why I am doing this? Just for MATLAB reasons. I mean, it was easier for me to do so. So that I am doing over somewhere over here. And let me not explain this. Is it okay if I don't? Yes? Nobody says no, so I will move on. So once I make this, I can run the code and I get the same behavior, right? Entropy reaches at some maximum. But if I compare the entropies derived from energy and the entropy derived from velocity distribution, not speed distribution, then you can see that they are quite apart. So this was our ignorance of ignorance. So we were ignoring the fact that we can be at different Vx and Vy's while having the same energy. Does it make sense? Yes? So are we ignoring anything else? When we look at all the velocities, Vx and Vy, are we still ignoring something about the system? The positions, very well. So we will see another huge gap between the entropy derived from both looking at positions and velocities, which will correspond to looking for particles in four-dimensional space. That's what we call phase space, right? So all the V's, all the momentas, and all the coordinates. That's actually the maximum information that the system is carrying, because if you know all the positions, all the velocities, then you know everything about the system. Does it make sense to everyone? Very good. Okay, let's move to that part. So this time I just did Vx and Vy. Now I am also including Rx and Ry. Okay? And this time actually I have Q floors, but each floor is four-dimensional. Okay, so it's something like this. They are all they are all orthogonal to each other, but of course I cannot draw in 2-dimension 4 vectors that are orthogonal to each other, right? So it's a 4-dimensional space. Again, I do the trick of using these m's and etc., m cubes. That basically brings those 4 dimensions, it unfolds them into 1 dimension. Okay? Believe me or not. Okay, let's say I did all that, and again, entropy is calculated in this simple way, like P ln P sum, and this in this case, this dVrxy corresponds to the volume element in that 4 dimension. It's dx times dy times dvx times dvy. Okay, and I have that expression somewhere over here. Do you see? Are you ready? So maybe you don't see the numbers. Do you see the numbers? So it's now in the order of 10 at point something, but before it was 3 point something. Do you remember? Come on. Okay, let me draw them together. So I could still take this one out, the calculation with respect to energy. I hope it works here. If it doesn't work, I will not do it, don't worry. No, it will not work. So never mind, you believe me. Thank you. So I have a very nice example to show you that you are indeed missing something when you look just at the velocities. So it's a typical example where you have a box, right? Let's say it's thermalized, so it's at thermal equilibrium, okay? Then suddenly you increase the size of the box, okay? What will happen? That's the question, okay? So if we are looking at the velocity distribution, once this, okay, let's run the code and I will tell you what the code is doing. So the code will have 3 windows, okay, something like this. One of them will show the particle distribution, okay. One of them will show entropy because of Vx and Vy, and the other one will plot entropy because of Rx, Ry, Vx, Vy. Does it make sense to everyone? Are you ready? So let me show you the code. So it goes from, it first thermalizes, it runs 10 steps of those Q steps. Okay, then that one finishes somewhere here. And then it runs another 20 steps with twice the volume. Okay, finally it will run another, it will run to 10,000 steps, but we will stop with doubling the volume one more time. Okay, and we will derive a lot of things from there. So let's run the code. It's a slow code, so we will have some time to talk about it. It should not be this slow, but so right now the volume is not changing, okay, and we are waiting for the system to settle at some equilibrium, okay. It's actually in the equilibrium, and you can see that you have your fluctuations, right, because of numerical accuracy. So constant maximum entropy. For all practical purposes, you can call it constant because it changes between 1075 and 1080, right? Now, at the step number 10, after the step number 10, suddenly the volume will double. Okay? Are you ready? Now the volume is doubled, and you can see that the particles diffusing the other way. Do you see them? So what is happening with the velocity distribution? It suddenly went down. Okay? Why? Because, okay, who can tell me why? Just think about it. Bilge?
The collision frequency is decreased. So there's less exchange of velocities between.
I never thought about it that way, but probably that is the one part of the answer. But notice that, first of all, let me ask you something, okay? If I have volume V and volume 2V, will the distribution of velocity change if I'm not giving energy or taking energy from the system? Same number of particles. It shouldn't, right? So eventually, after I increase the volume at the end, the entropy should be the same. The entropy calculated from the velocities. Are you following? Mm-hmm. But in between, there will be non-equilibrium, right? Notice that only equilibrium corresponds to maximum entropy. So since in between you are at non-equilibrium, you go down in the entropy, and you, it jumped again to the four times the initial volume, and you can see again a decrease in the entropy calculated from velocities.
But every time it would settle at the same point, right?
Yes.
Because we are calculating with respect to velocities. But for example, what if we calculate the entropy with respect to position?
Yes, that's this entropy.
That's always increasing.
Exactly. So you would so you can see that entropy should be the real one, the ultimate entropy that will go straight to our equations like S equals dq over t, ds equals dq over t, or I don't know, these thermodynamics equations like delta, you know them, right?
Delta something.
T delta S, etc. That S is the configurational entropy. So you have to look at the whole phase space, okay, and find the probabilities. Take PLMP. And for example, what do we expect that entropy to be in the case of sudden expansion of volume?
You mean the art of considering everything?
Yes. You may not know this, it's totally okay, but in this case, the entropy goes with ln of the volume, okay? So if you increase the volume to 2 times, then the change in the entropy is related to ln2. Then if you double it one more time, the change should be the same. So that was the message here. So I jumped from 10.8 to 11.4, right? The next jump, since the ratio of volumes are the same, has to be more or less the same. And it's more or less the same, I guess. 0.5, 0. Exactly. The true one is the one that you look at the whole, if you don't ignore any part, if you don't ignore any of your ignorance. So what I mean is that combining all of this, which means that you have to look at both velocities and the positions, and they are enough.
So in the end, we say that if we combine them, each of them take information from both of them, increasing the volume, then would increase the entropy.
Yes, Yes. So exactly. So if you are looking just at the velocities, you will not see the increase in the entropy, right?
But the real entropy increases.
The real entropy increases. So today, I think, by the way, all this I also learned last week by playing with this thing and realizing that entropy is not changing. What is missing? So I put the positions to, etc. So I even have a friend who studied this 3 times, and this is his favorite subject. And he had multiple revelations when I showed these codes. Like, I hope you are also getting them. So this is not all. I still have more things to share with you. So now I want to calculate these big properties like pressure, temperature, entropy, the real one, etc. Okay? How would you calculate pressure? Okay, here how I calculate it. So basically the pressure at each wall corresponds to, so when it hits and goes back, right? How much momentum is transferred? 2 mv, in our case this is 1, divided by dt. That's the amount of time. So this one corresponds to dp over dt, which is force, right? But we have to divide it with the area. But we are living in flatland. What is area in flatland? The length. So we divide f with the length of the wall, and that gives us the pressure applied to
flatland. You mean 1D area?
2D.
But the area is colliding to its. If the area, so the whole thing is 2D, but a wall and the areas corresponding, they are 1D, right?
Yes, exactly. Thank you. So you can see that expression over here. I added this, like this part calculates the collisions of particles with walls and pressure. Do you remember the collision parts? So whenever I have a collision with the wall, I also take care of the difference in the pressure. Okay? By the way, what I'm going to do in this case, I will start with some volume and I will slowly increase the volume. Do you remember the piston systems? So what do you expect? So you have a gas, you take the piston out. What do you expect? Pressure decreases, very well. What else? Temperature will also go down. Okay, what will remain the same if I'm doing it very slowly? Quasi-static process, like isentropic, exactly. So entropy has to be the same, right? Isentropic means this with the same entropy. Now you are confused because volume is increasing and but okay, we will see that the entropy will increase in this case with ln v again. So it's not isentropic. So what is wrong there? It took me a lot of time too. But luckily I have very smart people helping me. So first we will do something wrong, and it will account for isothermal process. Okay? Isothermal, because notice that it's a closed box, and just like before, we will have the same temperature. Do you agree? So what do you expect to get when you have the same temperature? Remember ideal gas, PV, nRT. So P times V has to be constant, right? And if you are not so ideal, which our thing is, it has some radius, etc., right? Then you are in a regime, in this so-called van der Waals gas, right? Then still you have something like P plus some number. I ran out of numbers. Let's say A. V plus B has to be constant. Can't you guess? So we are expecting something like this. Are you with me? Because of finite size of the balls. Okay. Do I happen to have run this program? Yes, I did. Okay. I ran this program for a lot of time, and I already have everything. So everything. You have the data. I have the data. Yes. So, for example, I will load the data, and I will plot log of volume with respect to entropy. ln V with respect to entropy. What do you expect to get? You mean a line that is that has. Okay. Let's see if that is correct. Yes, you get a line. Okay. So, what about the?
What versus what is this?
Okay, it's ln V versus entropy. ln V versus entropy. So if I do the linear fit, it's very close to 1. Okay? Are you with me? Yes, so things are going well. So what about the temperature? Let me plot the temperature. What do you expect to get?
The temperature versus what? So entropy. T versus S.
The temperature is constant. Isothermal system, yes. So now, then we realize that we need to have this correlation between P and V, right? P has to be, if we write down the equation, if we take it to the other side, this equation, then we need to have P related to V in a way that there is some A times V plus B to the power of N plus C. Okay, and what N has to be? -1. Yes, -1, because we took V to the other side. So I will do the fitting. I will take the X data as volume and Y data as pressure. Oh, sorry. It's over here. You can see that already it looks nice. Like as the volume goes, the pressure decreases. So let's fit this equation to the formula below, custom equation. Are you following? A times X minus B to the power of N. It couldn't fit, but because it starts from a bad place. Now, if I hinted to start with -1, maybe you think that it's cheating, so let's start with N equals -0.1. Okay? Still, the fit ends up with -0.999. Do you see? It's indeed an ideal gas expanded isothermally. Everything checks, right? So we are calculating entropy correctly, we are calculating the pressure correctly, P times V, etc. Very good. So what is the problem? Why? What are we missing? So basically, we expect the gas to get cooled, right? But it stays the same with the same temperature. So we need to give the system some energy, but we are not giving the energy anywhere, right? So what is missing is the following. Let's say you have a wall. You come to the wall while the wall is moving with velocity v or w, the wall moving with w. What we are doing is that while moving this wall, we don't take into account basically what we were doing is we were saying that the particles that hit that wall will come back with the same velocity. But that's not the case, right? Even if you are moving the wall very slowly, it will have effect on the particles that are hitting that wall.
Relative velocity.
Exactly. So in the end, you will get something like this: v minus 2 omega. Do you agree with this, everyone? So then you will get isentropic process. Okay. What do you remember from isentropic process? By the way, let me show you the code first. So I have this movement of the wall. Probably this is not 4 but 2, but anyways, I'm still working on it. But you trust me, right? So you can see that I incorporated this extra term that comes also in the calculation of the pressure, right? And also over here, whenever they hit the moving wall, they will not turn back with the same velocity but with less velocity. Okay? So I happen to have run this for some time, so I have this isentropic thing. By the way, I'm also calculating the work done, the heat, the internal, but I didn't have time to go through that. So what do you expect to have, what kind of relationship do you expect to have between the work done and the change in the internal energy? This is an isentropic process, so there is no Q, right? So the work done should go to the change in the internal energy, right? How can you calculate the work done? You can take the PdV integral. This is taking that integral. And this is looking at the change in the internal energy. Because you remember for 2 dimension, CV is equal to 2. So U equals to N times KB times T. But KB is 1. So I lost you, but never mind. So you can see that it's a line that fits. While the process is going, the work done and the change in the internal energy, they nicely fit into a line with a slope of 1. Maybe some point there, but just ignore that. Probably that comes from this 4s and 2s. Well, I'm very close to stopping boring you, okay? So what do you expect from isentropic process? Do you remember isentropic process, Bilge? Have you seen thermodynamics? Believe me, you know much more than people who saw. Now, I want to believe that.
I don't remember.
You don't remember anything. What about you? Isentropic process. What was the PV relationship? P times V or P times something else?
Not anymore, I guess. Because
There was something here, right?
Yeah, gamma. Yeah.
Yes. Constant. Very good. What was that gamma? It was CP over CV, right? So what is CV in our case? Remember degrees of freedom? So if you have 3 degrees of freedom, then 3 over 2. 2 degrees of freedom, 2 over 2 equals 1. How do you go from, well, this is 1R, right? If you don't remember, no, never mind. So in our notation, where everything is 1, CP is actually CV plus 1. Okay? Which gives you, normally in 3 dimensions, CV is 3 over 2, CP is 5 over 2. Right? In our case, CV is 1, CP is 2. Very fundamental knowledge, right? 1 plus 1 is 2. So gamma is
2. No, yeah. It's 2.
now you get stressed, right? No problem. So what we expect this time is to P to have something like A plus V plus B to the power of n equals to minus 2 plus C. Do you agree? The PV curve should have a different exponent. So let's again fit CF2. Do you really believe that I did actually make this and I'm not cheating? It takes some time for this to run. So maybe this can convince you, right? I still have imperfections here.
You just put them to
I passed them through some noise, right? Okay, custom equation a times x minus b to the power of n. What do we expect n to be? Minus 2. So let's start with minus 1. Okay. Do you see the fitting? It's minus 2. So you can see that we actually were able, with this simple system, just balls hitting each other, you can see that we can actually numerically validate many thermodynamical relationships. I think if you rewatch this, if you relearn this many times, you will have a very strong connection between what's going on microscopically and what's going on macroscopically. Okay, and that's very important connection because we have a huge gap, because the macroscopic one comes from 19th century, microscopic one comes from 20th century. It's like old generation and new generation having the fight all over again. Okay, however, they are talking about the same thing, and they can be brought together with computation. Do I have anything else? I do have some stuff, but let's stop here and now.